Now, starting the entrance part of the chemical kinetics. So we have seen the Arrhenius equation. In that Arrhenius equation, you have seen the equation is log K is equal to log A minus EA by 2.303 RT. In that equation, the of straight line with a negative slope, you have seen it. On plotting a graph, you have seen that log K against 1 by T, we get a straight line, and the slope gives the activation energy and the intercept gives you the frequency factor. Already we have seen that. So similar to this here also, I have done here two what you can say lines, you can see that straight lines. I have marked it as 1 and 2. Got it? See, this is the dependence of rate constant of on temperature for two reactions that we can see very well. You can see that two what you can say reactions are there. That is reaction 1 and reaction 2, and we are showing from this particular graph the dependence of rate constant against temperature. Now in the reaction 2, listen now carefully, the modulus of slope, already I discussed with you that the slope is negative here. Got it? In the Arrhenius equation you have seen the slope is negative there. Got it? We have already seen it in the Arrhenius equation. If you see the graph of the Arrhenius equation, if you recollect the graph of the Arrhenius equation, the slope was negative, and the slope gives the activation energy, and again I repeat, the intercept gives you the frequency factor, that is the y-intercept, we can say that. In this graph also which you are seeing it on the screen, that is the reaction 2, the modulus of slope. Got it? You know mod in maths you've studied. The modulus of slope is greater than that of the reaction 1. Alright, again I repeat, in the reaction 2, which you can see it from the graph, the modulus of slope, because here the slope is negative, so you will find the modulus of the slope which is greater than that of the reaction 1, so to say. And hence, for that particular reason, the reaction 2 has higher activation energy, and the reaction 2 will be more sensitive to temperature change. So if this sort of graph is given, then 2 has got higher activation energy than that of reaction 1. Got it? And the 2 will be more sensitive to temperature change. That means a slight increase or decrease in temperature will change the activation energy of the reaction. Rather, slight increase in temperature will change the activation energy of the reaction, because again I repeat, the modulus of the slope in the graph 2 is greater than that of the reaction 1. What you can say, graph 2, I am saying the reaction 2 is greater than that of the reaction 1. I hope you got it, this particular thing. Now the next which are seeing it is that the reactions on the basis of the influence of temperature. These are the different types of reactions which has been shown to you here. The rate against temperature, the first graph, the rate is not coming so clearly. So whatever it is, I am reading it out. That is, in the y-axis the rate is there, and the x-axis the temperature is there. In all the cases you can see the rate against temperature, but I have shown you the different type of graph. This is a normal reaction, the reaction which I was talking to you just now, we can say that. Now this one is an explosive reaction. First it increases, then it increases, and after that it remains constant, the rate. Then after that the biological reaction, the metabolic activities. Alright, the metabolic activities, the biological reactions you have seen in the surface chemistry, that is the chemizoption reaction, that sort of reaction we can say that. Clear? So first it increases, then reaching a temperature of around 45 degrees Celsius, that is slightly above the body temperature, then again it decreases, we can say that the rate decreases. Alright, clear? So these are the three different kinds of reactions. So why I am showing you the graph, because from the graph the question may come that what sort of reaction is being depicted, how the rate of reaction it's influenced on the basis of the temperature. So this sort of question comes. For that reason I have done it. So in the next reaction you can see it is the oxidation of the carbon is taking place, the oxidation of the carbon. Alright, so first what you can say, it is just like a sinusoidal curve, the rate against temperature, the oxidation of carbon. So how this particular thing is taking place, because when carbon is oxidized it may form carbon monoxide or carbon dioxide. So initially what you can find is that it increases, and after that the rate decreases, and again it increases. Why? Because there is a question of equilibrium. When it attains equilibrium the rate remains constant, again it increases because the temperature increases. So hence what you find is that with increase in temperature the rate of the reaction increases and decreases further, we can say that. So basically in oxidation of carbon this sort of reaction is taking place, because two types of reaction can take place, either carbon monoxide and carbon dioxide. If it is carbon dioxide it is quite stable, if it is carbon monoxide is again reversible, because carbon monoxide is an unstable product. For that reason the reversibility factor is involved here. Alright, and this one, the reaction which you can see the temperature, it is the only reaction with negative temperature coefficient. We can say that in most of the reaction the temperature coefficient increases. You have seen it. With the increase of 5 to 10 degrees Celsius, the rate of reaction becomes either double or triple. You have read it in the temperature coefficient. But this is the only reaction where the temperature coefficient is negative. That is 2NO plus O2 gives 2NO2. This is the only reaction, mind it, where the temperature coefficient is negative. Otherwise, in most of the reactions, almost all the reactions, with the increase in what you can say temperature of 5 to 10 degrees Celsius, the rate of the reaction either becomes double or triple. We can say that. Clear? So in this way, you can see that these are the different types of reaction, as you can see it there. Alright, that is nothing but the normal reaction. This is an explosive reaction. This sort of, first it increases, then the rate becomes almost constant. Temperature constant, it is, means it is what you can say, this sort of graph, after increasing, this sort of graph is nothing but undefined, we can say. And the biological reaction, the metabolic activities, is a normal oxidation of carbon, and this is a particular reaction. Okay, that is 2NO plus O2 gives 2NO2, where the temperature coefficient is negative. Next is this is expression for the rate constant for reactions of different order. Now see, the first two, that is the zero order and the first order, already I have derived this particular one in the regular classes. For the second reaction, second order and the third order reactions, also the derivation is similar. So derivation is not required. For that reason I did not do the derivation. Simply I have written the formula. You need to remember this particular formula for the second order reaction. If the second order reaction involves only one type of reactant, then the third reaction which you can see, the R is equal to K, A concentration of A square, or K is equal to 1 by T concentration of 1 by A minus 1 by A naught. And if two reactants are involved, it is also second order reaction, then R is equal to K into concentration of A into concentration of B. So the formula will be 2.303 by T concentration of A naught minus concentration of B naught log B naught into A by log concentration of A naught into B. And this is a third order reaction. As you can see, the formula K is equal to 1 by T concentration of 1 by concentration of A square minus 1 by concentration of A naught square. We can say that. So in this way, these are the expressions. You have to remember the formula, just like you have remembered for zero order and first order. You need to remember for the second order of one type of reactant and two different type of reactant, and next for the third order reactions, we can say that. So you just remember the formula of what? Rate constant. Formula of the rate constant, because otherwise R is equal to, that is quite easy. That's not a difficult part, but remember the formula of the rate constant. Now next is, as you can see, this is the plot of half-lives of different, what you can say, order of the reactions on the basis of its concentration. The plot of half-lives of different order of the reactions. The first is, you can see, it is zero order, then we have got the first order, then second order, then third order, so to say, in this way. Alright, so in the zero order, you know, the formula is T half is equal to nothing but A naught by 2K. So A naught by 2K, so it depends upon the concentration. Alright, in the first order, the formula is T half is equal to 0.693 by T half. We can say that 0.693 by T, that is T half. So there you can see that it does not depend upon the concentration, so it remains constant. It remains constant, we can say that. Clear? As it does not depend upon the concentration, so to say. Clear? So the what you can say, the graph remains constant. Similarly, for the second and third order, I have taken 1 by A. There the concentration I have not taken. I have taken 1 by A and 1 by A square. So hence in that particular case also it depends upon, as it depends upon, so hence you can see the zero order, second order and third order, they have got similar sort of graph. And the first order, there it does not depend upon, because the formula is 0.693 by K. Hence it is independent of. What is independent? The concentration is independent of. Got it? So this one. Next, after that, we are having some linear plots of reactions of different order, we can say that. So just you have to remember this particular thing. For the zero order, you can see as the graph is negative, the slope is negative. So in the zero order and the first order, the slope is negative. Got it? So hence as the slope is negative, just now I told you the formula. We can see K is equal to 1 by T A naught minus A. If you relate with Y is equal to mx plus C, then you will find the slope is negative. Got it? Same thing for the first order also. You can see K is equal to 1 by T 2.303 by T log concentration of A naught by concentration of A. This also equation, if you relate with y is equal to mx plus c, you also find the slope is negative, minus 2.303 by T. I hope so. This sort of you will be getting it. The slope is, and the second order and third order definitely depends upon, and the slope is positive, we can say that. Same thing for the integrated rate equations for the rate against concentration. The first graph is against concentration against time, the second graph is against rate against concentration. So R is equal to K into concentration of A naught for zero order reaction, that is independent of concentration. So it is a straight line parallel to concentration axis. But in all other order, you can see rate depends upon concentration. For first order, R is equal to K into concentration of A. Second order, I have told you just now to you, you can see R is equal to K into A square, it depends upon. R is equal to K into A into B, it depends upon. For third order also, R is equal to K into A cube, it depends upon. So it depends upon concentration. So hence, for that purpose, it is a straight line graph equally inclined to both the axes. Remember that the graph is said the second, third and fourth graph, that is first order, second order and third order, you can see the graph is equally inclined to both the axes. It is set as, which is rate against concentration. So these are the things which you need to remember. You will be getting the question, the short question upon the graph. So hence I discussed with you. Thank you.